Okay, shall I let everybody in then? It's 1 minute
Yeah.
past. So, yep,
Oh, good.
here they come.
Evening, David. Everyone
Hi,
else.
Roger. First,
Oh, we're so
first of all,
Did
close.
you keep me back for the last person?
Right, we're so close.
no, it's turning into a competition now. Who can get in before Roger?
Well, put
Hi,
me in
Brad.
last.
Nobody's managed it yet.
I was literally holding the button like unmute, like hi, and no.
I had my cursor at the right position.
I think this is going to run and run. This is a good one.
I think you're using cheat codes, Roger.
And then,
I think you've got some sort of cheat codes going on, some sort of robot waiting for you.
Well, I must admit, Roger did come in as soon as I opened the meeting, so I don't know whether you get an alert or you're just sitting there hovering and waiting.
I've been waiting since 22.
That's what time I logged in. I thought that was a sure win.
That's even keener than me. Come on.
Everyone else okay?
Good, thanks.
Good.
Hi, Brad. How are you?
Yep, seeing a few friendly faces there. Hello, Rachel. Hello, Julian. Put my note there.
Hello.
Absolutely awful weather here.
Oof.
Yeah, same here.
It's a shocker here as well.
Takes the wheelie bin up the road. Well, not really, but nearly. Yeah.
There's been about 70 trees down in Gloucestershire so far today.
Is there?
I've gone and put a gigantic rock on the base of the trampoline because it looked like it was thinking about taking off,
Migrating.
heading off to the neighbors.
Good stuff.
Are you back in
Anybody?
the department yet, Brad?
Sorry, what was that?
Are you back in your department yet?
No, one or two labs have reopened, but we're sort of in the midst of still, we're going building by building rather than area by area. And
Right.
I think the rest of our labs will open up in the next 2 to 3 weeks. But we're low group on the totem list. So I think we're sort of next. We're doing the paperwork now.
Right. Yeah, I think our building's open, but nobody wants to go in, so they can all work from home.
Yeah.
Well, if we can, why not?
Main physics people back in because, the experimentalists are.
Right. Okay then, folks. Let's. Shall we crack on? So, just to give you an update on where we are. Thanks to everybody who's put the pictures on the Padlet. So we've got plenty there to go through as and when we get a spare minute to go and look at some of these stunning pictures. And we've got a couple of 2 or 3 superstars as well, but had their images published in magazines this month. So well done to you guys. So just looking forward to the next lot of meetings. So next Tuesday we've got Nick Hewitt and Sean Reynolds. Nick's going to tell us about nebulae, and Sean's going to show some of his nebulae images, which will be great. Looking forward to that one. Week after, we got Martin Hardcastle, who's going to be talking about surveying the sky for radio galaxies. And then we're going to have a general meeting on the 15th. So over to you, folks. So any ideas, anything you want to contribute, let me know so we can organise something for that. And hopefully we'll get some clear skies. Is it a bit darker? It should be a bit darker by then, shouldn't it? So might get some live streaming. Who knows? And then the week after that, it's on the Monday. That's why I put it in red. And Paul Mann is going to talk about images of the universe. That's going to be part 1. He's going to do a part 2 at a later time. And then 29th, again, another general meeting. So any suggestions, throw it my way. And then going into October, missing a meeting. So I haven't quite worked out what we're going to do with that one yet. But on the 6th of October, we've got Pete Williamson, who's going to do Herschel to Hawkwind. So lots of music, so lots of astronomy-based music. So that's good talk as well. So yeah, good fun. So I've been busy trying to get some speakers sorted for you. So tonight's meeting, we got Professor Brad Gibson, who's director of the Milne Centre for Astrophysics and head of the Department of Physics and Maths at the University of Hull. Is that correct, Brad?
That is indeed.
And leads research, education and outreach groups, and is a expert on galaxy formation and evolution and complex biological life in the Milky Way. And he's going to tell us all about, I'm intrigued by this one, liquid mirror telescopes, wave of the future, or just a ripple. So if everybody else can, I'll just mute everybody for a minute. Hold on, where's my participant list gone? There it is. So I'll just mute everybody. Hold on. There you go. And Brad, if I unmute you, there you go. I've asked you, you should be able to unmute yourself.
Should be okay.
Yeah, okay, so if you'd like to share your screen, everybody else can turn off their videos. That would be great.
I apologize. I know there's probably one or two of you who have seen a version of this before. Possibly Rachel, I think. But here we go. So for me, first, thank you very much for letting me come and talk to you about this. For me, this is a blast from the past, if you will. It represents 2 to 3 years of my life when I first started my postgraduate degree back in Canada. So it would be like the late 1980s. And I was finishing up my undergraduate degree, trying to make a decision on what I was going to do afterwards. And an article came out in Scientific American about this was the very beginning of the time, the search for extrasolar planets. And it was, a fascinating article, caught my attention. Being a science fiction fan, it tickled my fancy about thinking I could be involved in the first searches, the first real dedicated searches for extrasolar planets. And so I had made the decision that that is what I was going to do. Now, the reason I chose to go to the University of, let's see if we can get this to work. I chose to go to University of British Columbia because the authors of this article in Scientific America were from UBC. And they designed a very clever way to measure the spectra of stars with incredible precision to look for the gravitational influence of planets going around them. And like I say, that caught my attention. It sounded like a high-profile, exciting, cutting-edge project. Be sort of the first to be involved in these sorts of searches. And when I got to the university, this is the scientific paper which really motivated it. I won't spend a whole lot of time talking about it. I sort of gave you the gist of how these searches for planets worked. If one reads through this paper, this was the first paper that actually really discovered a bona fide extrasolar planet. The problem is if you go and read the paper, what you find is that they couch it with a lot of question marks. They eliminate all the obvious things that they see in the spectra that it might be due to, and they have a very soft conclusion that it's extrasolar planets. And it got a lot of attention. Like I said, it coincided with their article in Scientific American, but they were just a tiny bit too cautious in questioning their conclusion. And so it sort of lay dormant for a number of years until the next generation of extrasolar planetary searches came along, which have now discovered thousands of planetary systems. And unfortunately, this sort of pioneering work was a little bit lost in the shuffle, even though they did go back and confirm everything that they had discovered. And it's one of those cases where, maybe this is the nature of being Canadian, is they were just far too cautious. And if they'd been a little bit more ambitious and bold in what they had stated, this would have been the first discovery paper that was recognized and acknowledged. It was acknowledged by those who did win the Nobel Prize for discovering extrasolar planets. They nodded towards this paper of Campbell, Walker, and Yang, and admitted that they really did discover it, and it was just a matter of timing and how they sold it that led to one group winning the Nobel Prize rather than this group. But anyways, this is what attracted me to Vancouver. This is what attracted me into astronomy and astrophysics. When I got there and sat down and started the project, it took me a couple of days before I realized it was not quite as exciting and engrossing as I thought it was going to be. It's highly mathematical, doing things like time series analysis, trolling around in very noisy, messy spectra, trying to find evidence of wobbles in the spectra due to planets. It wasn't quite the exciting exploratory science that I thought it would be. And so I made the decision after that first week of my postgraduate degree to step away from extrasolar planets, thinking it was boring. Now, of course, I look back now with hindsight and realize that was probably the biggest mistake of my scientific career. I've still had a good scientific career. I've got no real complaints, but I missed that opportunity to be in that pioneering first group in the search for planets. But what did come along was this project that you can see there on the front, and it's this thing called liquid mirror telescopes, which I will spend the remainder of the scientific part of the talk going through exactly what they are, why they attracted me, their strengths, their weaknesses, where they stand today. But it was the sort of thing that my supervisor was able to hold up in front of me, and it looked like the exciting sort of state-of-the-art, never tried before experiment that I was looking for in my postgraduate work, which is what attracted me to it and to jump ship from the extrasolar planet community. So, but before that, just let me say a few words about where I'm based at the University of Hull. If I was sitting there now, I'd probably do a quick poll and ask people to raise their hands as to how many people had actually been to Hull. It's always a fascinating survey to do. First thing that I want to say is that the E.A. Milne Center for Astrophysics is named after E.A. Milne, not A.A. Milne. One of the probably the most common questions I get. They are different people. Alan Milne, the creator of Winnie the Pooh, is not Arthur Milne, the namesake of our center. Arthur was, they do have some interesting parallels through their experiences in World War I. Alan Milne from Winnie the Pooh fame in the Army, and Arthur Milne in the Navy Reserve. It's named after, our center's named after Arthur. He was born and raised in Hull. He was a contemporary of Einstein, good friend of Einstein. They spent a lot of time talking about cosmology, their various perspectives on cosmology. Arthur was a very clever mathematician. He wanted to serve in World War I, but was unable to due to what we now recognize as early onset Parkinson's. But what he did do during World War I was he was seconded from Cambridge, where he was at this point working on stellar astrophysics and stellar atmospheres and how energy propagates from the centers of stars through to the outer atmosphere and beyond. And he was, as I say, seconded to Portsmouth to the HMS Excellence, the Naval Reserve group, where he took his knowledge of stellar atmospheres and applied it to the Earth's atmosphere, and in particular using what we call echolocation, kind of a triangulation by sound. It was the first war, if you like, that was fought in 3 dimensions, where you had to worry about things that were coming in, not just along the horizon, but planes and zeppelins, and particularly in the South Coast, worrying about planes and zeppelins coming in under cloud cover or thick fog. And so sound was the way in which you would inform the gunners as to the optimal place to point weapons. And so he developed, with a group of astrophysicists, this anti-aircraft gunnery technology. And if you go to his Wikipedia page, you find more about that than you do about the work that he did on his alternate theories of relativity and his work on stellar atmospheres. One of the most decorated scientists of the 20th century, one of the few to have won this triumvirate, sort of the triple crown of astronomy prizes. When I moved to Hull, I guess that was 5 years ago, I had done a quick Google search of famous people from Hull. It's a very short list, but I recognized Arthur Milne's name and thought it was a great opportunity to set up a research center building on his legacy at Hull. His daughter, Meg, you can see here in this picture, had just published a biography at that time of her father, and I worked with her and her granddaughter and Arthur Milne's granddaughter in the establishment of the center. We've been around coming up on 5 years now. We've gone from, I guess, 0 to about 25 staff and postgraduate students in a very short period of time. And our research sort of spans everything from solar physics to large-scale structure. The majority of our work is based around modeling and access to high performance computing, and the investment in a large supercomputer on campus from the university was one of the lures to bring my group from central Lancashire, where I was based before. We have effectively 90% access or so to Viper, which is one of the most powerful facilities in the country, owned by a single university anyways. We also have a share you recognize this chap here. Stephen and I are co-eyes on a grant with the UK government that funds the national cosmology supercomputer Cosmos, and we maintain a small share of that through the agreement with the department that funds that. So that underpins a lot of the work that we do, is high performance computing and applied, like I say, everything from primarily the origin of the chemical elements through to how those elements get distributed around galaxies. We call it galactic archaeology. That's a topic for another day altogether. We work closely with some people that no doubt most of you will recognize: the Queen's astronomer, the Astronomer Royal for England, Martin Rees, Jocelyn Bell Burnell, the discoverer of pulsars. Jocelyn, on one of her recent visits to Hull, she took some of my students out for dinner. And Helen Sharman, the country's first astronaut, born not too far from here, down the M62. Helen was here. She comes up once or twice a year, comes into schools and colleges with me. Was here as part of the British Science Festival. And again, here she is with some of our students. This is not one of our students. This is my daughter Esme, who, if you hear any screams of terror downstairs, is playing on the Nintendo Switch right now and gets a tad invested in the game. So I apologize in advance if you hear any screams of that nature. And more recently, Michael Foale, probably the country's most decorated astronaut. Again, born not too far from here. He's one of the few astronauts to have spent more than a year in space. They're not there in name just because they're famous. They're there because they have the same underlying philosophy, ethos about trying to widen participation and diversity, and take a lot of pride in working in this area. Around Hull is one of the poorest cities in the country. I think it's the poorest city in the country in terms of, second poorest city in the country in terms of household income, where only 10% of 16-year-old boys go to university. And so there's a lot of challenges in the region, which is what attracted me in the first place, feeling that we could make a difference. And each of them sort of commit some fraction of their time to come into schools and colleges with us. Not about recruiting students to come to Hull. It's about just providing that level of inspiration to keep them excited about the STEM subjects as a whole. So it's one of the nice perks of the job is having them along with us for the ride. We do, as Dave mentioned on the first slide, we do a lot of outreach and engagement, just as I know Dave does, just as Julian Onions, who's sitting here, does as well. Over the last 4 years, we do about 100 events per year. I do about 80 events, ranging from things that we're doing tonight with astronomical societies through to various things like the Royal Institution of Great Britain. A lot of the, this big number of 3 million is driven by things like our online work, my TED Talk and others within the Milne Centre who've done comparable sorts of things. Like Dave, we also have a mobile planetarium. We've done about 100 shows over the last 2 years. So we've reached about 3,000 students. Basically, all I've done is hand over the facility to a number of our undergraduates. They design the shows, they present the shows, they work with teachers around the region to do sort of shows by design, depending on whatever material they may be working on, whether it's at primary level or college level. So bespoke programs. They've been absolutely fantastic. And again, one of the things that we miss terribly over the 6 months while we've been in this lockdown is the inability to take those students out into schools and colleges and engineering and science fairs and allow them to do the things that they're so excellent at. And just sort of the last thing I want to say before I move on to the science bit, as we probably recognize, the space sciences, astronomy, astrophysics, the subjects that sit along the end of what we call the STEM spectrum, where physics and maths, computer science, engineering sit, there's a wide gender split, if you like, in physics. If you look at universities, the Institute of Physics, the numbers look like 22 to 23% at the undergraduate level are women, vast majority are men. It's not wildly different when you go and look at maths and computer science and some of the other areas that I just mentioned. This is not unique to Hull, it's not unique to the UK. It's sort of a widely recognized endemic problem that has multiple reasons for it. There's no simple one single solution to try to improve the demographics. At Hull, when I arrived here, it was about 10% of the cohort were women. Now, we've worked very hard over the last few years in collaboration with 20 or so colleges and secondaries around the region to provide, for example, research internships for students. We take maybe about 15 secondary and college students per year, roughly about 3/4 are women. We don't focus on the A-star A students that sort of have their careers already set in place, if you like, as to where they're heading, but we focus on those B, C, and D students who are passionate about sciences, haven't had maybe the right opportunity to get engaged in an environment that could help foster that passion. It's been good for our recruitment. It's not why we do it again. It's more about just reaching out to those students who would otherwise perhaps get lost in the shuffle, providing them with that opportunity to excite them about the subject. And I've been very lucky that I've had a number of undergraduate students who have the same sort of passion for trying to widen participation and diversity. When I go into schools and colleges, like I say, which I do maybe 60, 70, 80 times a year, I typically take some of my students in with me and they tell their story. Most of them have come from a similar socioeconomic background to the students that we focus on. And so they provide sort of the peer role models that, to be honest, probably play a much bigger inspirational role than the celebrity role models, if you like, because they are students that they can relate to. And, you know, we've just learned very recently that one of our students, Kiri Newson, was one of the inaugural Jocelyn Bell Burnell scholarship holders given out by the Institute of Physics in recognition of the role that she's played in engaging with schoolgirls around the region and committing to women in STEM initiatives, as well as coming from a very challenging socioeconomic background. So in some sense, this is probably the thing that we've taken the greatest pride in, doubling the number of women into physics at Hull over the last 2 years. And the project, that it's umbrellaed under this changing face of physics, was named by the UK Equality Challenge Unit as best practice in the country last year. So regardless of the science that you're going to hear about, the teaching that we do, if you ask me to put hand on heart, the thing that I'm most proud of, it's the work that we've been doing in terms of widening participation. So because it was the first time I've spoken to most of you, I decided I would take those first 10 minutes just to give you some context and background as to who we are, as we're hidden away up there in the Northeast on the Humber, and many of you wouldn't have been aware of what it is that we do up here in Hull. So now, back to the topic. So I've given you my motivation for why I ended up at the University of Hull, which was initially extrasolar planets, and then I got lured into the promise of what looked to be a cutting-edge project based around mirrors made out of liquids. And so it sounds like a strange topic, but at the time was very cutting-edge optical sciences. I'll show you a little bit about the motivation, why we were trying to do that. But first, I've got this sort of 1 minute long little video that will show just a reminder as to how large mirrors are made, just to contrast what I'm going to be talking about shortly when I move on to liquid mirrors. So here we go.
With a mirror blank, a cylindrical piece of glass or ceramic with low thermal expansion. The blank is ground so that the optical surface has the correct curvature. This is by far the biggest chunk of work. The optical surface is then polished to be very smooth. Lastly, a reflective aluminum coating is applied. In the early 1980s, Stewart Observatory Mirror Lab at the University of Arizona began using the technique of spin casting. This involves creating the mirror blank in nearly the correct parabolic shape in a spin caster that is a combination of oven and merry-go-round. Chunks of glass similar to Pyrex are heated in the device and once molten are rotated at a precisely calculated rate. Centrifugal forces produce a parabolic shape, and then the mirror blank is cooled and allowed to solidify while still rotating. This greatly reduces the labor needed to grind the mirror into the final correct parabolic shape. The following demonstration is useful for conveying how spin casting works. It consists of a thin rectangular tank, think fish tank, that is mounted on an electric motor that will allow it to rotate. A liquid is needed to represent liquid glass, and we will use water with a little green food coloring for visibility. Imagine that there is a built-in furnace, and temperature will be conveyed by a red glow. We can think of this as a slice of the normal spin casting process. We begin spin casting at room temperature with no rotation. Our glass is a rectangular slab. We then raise the temperature until the glass becomes molten, and then turn on the rotation. Note that our liquid quickly assumes a parabolic shape. We now turn off the heat and allow the glass to slowly cool and solidify.
So that is the premise behind how large monolithic mirrors were constructed through the 80s, 90s, and even today in the Steward lab. Just turn that down a little bit. Now, you can imagine replacing that liquid here with something that is reflective, and you can see the way it's paused there. It's a nice parabolic shape. If there is some coating or some liquid which is reflective, you've got a very nice parabolic mirror. And that's really the physics behind how a liquid mirror works. Now, instead of rotating sort of the liquid glass, as is done in the spin casting process, what we do is we take a vessel, sort of shown here or here on the right, and we connect a drive motor to it, start it rotating, and pour a little bit of some reflective liquid in this case mercury. And as the thing rotates, that mercury, just like in the movie that you just saw, will naturally take the shape of a parabola. The only physics, it's very, very simple physics. It's actually laid out in Newton's Principia, published 350 years ago or so. And the only forces that are at play when you start rotating a liquid is you've got gravity, which is recognized here by these arrows pulling us down, pointing downwards. And as it starts to rotate, you see this centrifugal force, sort of, if you like, pushes things out, thinking of a centrifugal force that way. And provided you are rotating at a constant rate, it will settle down into a parabolic shape where the gravity and the centrifugal force sort of steady and balance out. If you rotate it faster and faster, it becomes even more parabolic, or if you like, the F ratio changes, the focal length reduces. So if you double the spin rate, then it becomes even more parabolic, if you like, and that reduces the focal length. If you double the spin rate, you reduce the focal length by a factor of 4. And so by adjusting the spin rate, you can change the F ratio of your mirror. And if you want to keep it really simple, you just stick some sort of detector up there at the prime focus, and you can take pictures. That's great. Now you can immediately start to see some limitations of a liquid mirror telescope. The physics is dead simple. What that means is that there's not really any moving parts. That means you can build a mirror relatively cheaply. So, and that was ultimately the premise of my postgraduate work when I started, was could we make a 3-meter class telescope, so sort of a world-class professional level scale telescope in terms of size, but do it for less than 10,000 pounds. So that was our goal as we set out to do. And by not having any moving parts, by not having a complicated dome, by not having complicated correctors, at least in theory, this is what we could do for 10,000 pounds. And I'll show you how successful we were later on. But you can see sort of the limitation. If you take a liquid and start rotating it, that's great for looking straight up. You've got a nice parabolic mirror that's pointed straight up. But if you're interested in looking at something over there, or tracking and moving, this is what you cannot do with a liquid mirror telescope. You can look up, and you can only look up. That means you are restricted to the Earth's rotation and whatever passes overhead through the zenith. And the secret behind it, if you like, is that you have a CCD up at the prime focus. Your image hits the CCD, and you read out the CCD, not like you would do conventionally, where you might take an exposure for 10 minutes or an hour, or however long, then close the shutter and read the CCD out. What you do is you continually read the CCD out at the sidereal rate. So you are reading out the CCD at exactly the same rate, the sidereal rate as stars are passing along the columns of the CCD. So at the end of the night, you have a long, thin image if you've got a nice, dark, clear night. So that's basically wraps it up into sort of a Twitter level discussion as to the physics behind a liquid mirror telescope. Now we'll go into a little bit of the gory details and hidden secrets behind them. So first question that often comes up, and it's one I had to think about, was where does liquid mercury come from? Well, it comes from stuff like this sort of ore. This is cinnabar, mercury sulfide, if you like. And it's mined primarily, the vast majority, but 90% or so of the world's mercury is now mined out of China. And up until the 1950s, it was recognized immediately just how dangerous mercury is. Some of us will remember, being in school, way back in the day and having demonstrators or instructors in school playing with liquid mercury, pushing it around. We all thought it was very amusing at the time. Obviously, a very dangerous habit to get involved with. And it was recognized by all governments that it was a very dangerous material to mine. Until the 1950s in China, which is where most of the mercury does come from, it was only the prison population was used to do mining up until the 1950s. And what you do is you take this ore, cinnabar, and you put it into an oven, you heat it up so that you vaporize the mercury in the mercury sulfide, and then once it's vaporized, you cool it back down again, and you capture as it condenses out the mercury vapor back out into liquid form. And that's basically how you get liquid mercury. It's nasty stuff, as I'll come back to towards the end again. Now, we use liquid mercury for a few different reasons, primarily because it's highly reflective. One thing to remember, and I'll come back to this point again because it's very important, is that liquid mercury, normally you might be used to it maybe from having an old school thermometer that had liquid mercury in it. But if you need a lot of mercury is very dense, it's very heavy. So, if you've got a pint of beer, you know exactly how much in your hand that would weigh. Now, if you took that beer out and replaced it with liquid mercury, then your pint would weigh about 17 pounds. So it's very dense, it's very heavy. This will come into play when we start pouring liquid mercury onto our mirror cell to try to form that parabolic shape. If you have too much mercury on there, then it flexes the thing that you're trying to prop up, because it becomes very, very, very heavy. So that's one thing to remember, it's very dense. As I said, one of the reasons we use mercury is because it's reasonably reflective. What I'm showing here, this rather busy plot, is a measure of how much of the light is reflected from here on this side. It's a freshly illuminized mirror, this 4-meter telescope in Chile at CTIO. The different colors here refer to sort of the blue part of the spectrum and the red part of the spectrum. The details don't matter. So when you freshly illuminize a mirror, the reflectivity, about 90% of the light that hits the mirror is reflected. And as time goes by, because of various oxidation effects, because of just dust and silt and things accumulating on the mirror, the reflectivity declines. This is a sort of a 2-year window where you see the reflectivity drops by maybe 10% or so on a mirror. And then typically on this sort of time scale with these large professional class telescopes, then they will do a detailed, expensive cleaning of the surface. It may just be, in this case, a CO2 cleaning. It may be where they have to completely re-illuminize the mirror to get the reflectivity back from 80%, say back up to 90% or more. Now, liquid mercury is not as reflective as a freshly illuminized mirror. It has a reflectivity of about 80%, which on this plot would be sort of around here. The good thing about liquid mercury, in some sense, though, is that you can clean it more or less as much as you want from the mirror. So if bugs land in the liquid mercury and get stuck, or dust falls on the liquid mercury and gets stuck, you can, if you like, in the morning, stop it rotating, so you get a pool of mercury in the middle, and you just take a skimmer or effectively a mercury hoover, and you just take all the dust and bugs and things that are stuck and start it spinning up again, and you maintain that perfect reflectivity at 80%. So it's never as good as freshly luminized mirror, but it doesn't degrade with time as well. So there's a degree of stability there. That's a good thing about mercury. One problem is, I said right at the beginning, we were trying to build a 3-meter class telescope and do it for 10,000 pounds. So the first thing you might think of is you can buy the materials to make the mirror cell, which I'll show you in a second. But one of the things you do need is liquid mercury, of course. Now you can go online. This is one that I just pulled up, more or less the first thing I pulled up when I Googled it. To Nova Elements, if you wanted to buy liquid mercury from them, you can buy them in these small little ampules. This is just a 2-gram ampule, and you can see at the time when I pulled this over, it was about 45 euros for that little bit. So if you convert that into per pint, that's about 150,000 pounds. Now for a 3-meter class mirror, you might need 20 pints, let's say. So that'd be about 3 million pounds if you bought them in all of these little ampules. You can get it cheaper if you buy it bulk, but right away you've blown out the budget, which was to keep everything to less than 10,000 pounds. So you can start to see, you've already reached one problem here, is that the liquid mercury makes this thing prohibitive if you want to buy this sort of high quality liquid mercury. Now, there are other ways you can do it, and this is how I did it for my project. This was at a time when health and safety risk assessments were, if anything, maybe only lip service was paid to them. I was a fresh-faced postgraduate student, didn't really know any of these sorts of things. I just did what my supervisor told me. And one of my first jobs was to take the department truck and head out about 30 miles outside of Vancouver, where I was doing my PhD, to an industrial estate at 3 in the morning, where some people wheeled out large pallets that were filled with about 30 or so of these pint-sized containers of liquid mercury. Don't remember the name of the company, anything to do with that, but we were able to take all of the liquid mercury off their hands. It was not contaminated in a dangerous sense, but contaminated with with sort of silt, dust, things that made it not useful as an industrial lubricant any longer, but it's fairly expensive to clean if you're doing this in the industrial environment. And so we took it off their hands, these 30 or 40 pints of liquid mercury. So that reduced the cost from 3 or 4 million pounds for the liquid mercury down to 0. Eventually, the university did catch wind of these things and put a halt to that. But me, as a fresh-faced postgraduate student, naively just picked things up. Didn't really question why I was going to an industrial state at 3 in the morning. Just did what I was told. Now, there are some alternatives to liquid mercury that people have postulated about using in the literature that aren't quite as nasty as liquid mercury. And one of them that really could be used is what we call eutectic gallium alloys. Now, liquid gallium would be great because it's not anywhere near the danger that liquid mercury possesses. But the problem is gallium is only liquid above 30 degrees centigrade. So unless you're sitting in a tropical environment where it's very hot, it would solidify, which means it's not particularly useful as a liquid mirror. Indium is another one, but it's only liquefies above 160 degrees centigrade. So these things are reflective and safe, very expensive, but not really liquid at the right temperatures. But when you mix them together, this is what a eutectic alloy is when you mix two things that have high melting points, and then it reduces their melting point. So if you take gallium and indium and tin and mix them together, for example, their melting point is minus 30 degrees. So you can use them in more or less any environment, and you would have a safe alternative that doesn't have the issues associated with mercury and mercury vapors. The downside is it doesn't help in terms of keeping the cost down. These eutectic alloys are very, very expensive if you start needing 20, 30, 50, or 100 liters worth of them. So you again very quickly move into the realm of exceeding the cost of making a glass mirror, for example. And then at that point, you sort of defeated the purpose of having a liquid mirror telescope. If you can't do it for orders of magnitude cheaper, why would you do it given all of the dangers? So that's why these eutectic alloys were not embraced, simply because of the cost. So if you look at the history, like I say, the physics, the science behind it was outlined by Isaac Newton back in Principia. The first attempt, or the first discussion of them in a telescope environment, was a Jesuit priest, the Vatican Observatory, Ernesto Capocci, who in a series of letters outlined in a theoretical sense how you might build a liquid mirror telescope. I had some friends in the Vatican from my time as working with the priests as part of Vatican summer school, the observatory summer schools that they run. We couldn't find any evidence that Capocci ever took it from concept into the lab. There are some claims from Carrington and Henry Skye, a UK astronomer who emigrated to New Zealand. It's a bit vague as to what exactly they built. The first one that's really well documented is from Henry Skye, again, an astronomer from Surrey who moved and helped establish the astronomy group in New Zealand at Dunedin. And he has a well-documented 35-centimeter mirror that he built in the lab, did a lot of optical tests of them, showed the quality, the stability of the images that you could get inside of the lab. Then there wasn't a whole lot done for 35 years or so. And Robert Wood, in a series of papers, sort of 1908 through 1910, outlined his experiments in the lab. But this was the first case of one being taken out into the field. It's a half meter or so in diameter that he took out to his farm, upstate New York. And for those of you who've not read a professional journal, if you read professional journal articles now, you can look up one of Julian's papers or one of mine. They have a tendency to be written in there's a professional technical style that is very dry and very boring, but that is how scientific papers and scientific writing has evolved. But if you go back and read Wood's papers from 100 years ago, they're a classic example of 100 years difference in writing style. It is much more of a travel log, how the weather was when he left his lab at either Cornell or Columbia, I forget which it was now, and moved out into the countryside, whether it was sunny, talks about his farm. And it's a fascinating, interesting read, very different than the contemporary scientific articles. But if you dig into the article, you can see very much the success, what he was able to accomplish. And I'll show you one example of that right towards the end. But after that, there really wasn't a whole lot done until Ermanno Bora in the early 1980s in Canada sort of came back to the concept of the liquid mirror telescope. And Ermanno spent probably the next 25 years or so of his career working largely in the lab on the development of these LMTs. There was a couple of attempts to put things out into the field, which didn't really quite work. But his work in the lab really opened up the field and brought the field back into light. And he approached it the way that modern contemporary opticians, optical shock tests would do in the lab, in terms of measuring things with scatter interferograms and measuring things like the Strel ratio, and really characterizing how good you could make a liquid mirror, at least in the lab. And that's where we came in when I started my master's work with my supervisor, Paul Hickson, in Vancouver. It was to take some of the things that Ermanno had done in the lab and really have a functioning observatory, not just a single one-off experiment where you just take a single snapshot, but have something that actually collected data and did some real science to see, again, if you could construct something on the order of a 3-meter class telescope, again, very cheap, but actually have it be competitive with a glass 3-meter mirror in an observatory that might cost 100 times more than the liquid mirror telescope. So there's a few things that you have to be concerned about. The obvious one I mentioned right away is that you have to look up at the zenith. You cannot, whether it's rotating or stationary, if you tip a liquid over, it's going to pour out. So that's one obvious limitation, and I'll come back to that in just a second. But there's some other weird limitations or things that you have to be at least aware of when you're working with a liquid mirror telescope. And one of them and these are things you don't need to think about really when you have a traditional glass and freshly illuminized mirror, largely because a liquid responds to the various forces on it in a different way than a solid will. And one of the things you have to worry about is the curvature of the Earth. Now, remember, right back to the very first cartoon that I showed you, one of the assumptions, and it goes into Newton's work, is that the gravitational field lines drop straight down and are parallel to each other. And for the most part, that is true. But you can imagine, we do live, whether you like to admit it or not, we live on a spherical body. And what that means is that the lines of gravity, they point towards the center of the Earth. And if you're standing at one particular point, the line, the normal, if you like, to the surface is not parallel to the line beside it, if you like. And so what that means is, as you make a bigger and bigger and bigger mirror, that means that the lines of gravity, if you like, are not parallel to each other. They're a little bit off from each other. Now, for small mirrors, it doesn't really matter. If you start to get to really big mirrors, people start to think about, could you build, for example, 100-meter class? If you had the 100-meter class liquid mirror telescope, then those lines are sufficiently no longer parallel that it changes it from a perfect parabola. It introduces spherical aberration into the system. Now, you can correct it by having an appropriate, just like we do with our glasses, by having a corrector at the prime focus. But that is something you have to bear in mind. It's also a liquid, so you have to worry about things like the tides. It's not a big effect, but as the moon goes around, if you've got a liquid mirror there rotating, it does cause the liquid to respond. And so it does introduce a little bit of coma. Now, if you're at a bad site where seeing is terrible, like ours was in Vancouver, these are very small effects, so we don't really have to worry about them. If you're at a world-class site with sub-arc second seeing, these sorts of things do just get to the level of being measurable. Now, the one that is a bigger one that we have to worry about is what's called Coriolis force. And Coriolis force, you can think of it as if you're standing on the Earth, if you're standing at the equator, you're moving at roughly about 1,000 miles per hour as you go around. You can imagine standing at the pole as the Earth is rotating. For someone looking at it from the outside, you're not moving, you're stationary, so you're moving at 0 miles per hour. And depending on the latitude you're standing on, you vary from 0 to 1,000 miles per hour. And so it makes it look, the Coriolis force affects all kinds of things. It makes things look like they're moving in a curved path if you're standing from the outside looking at it. Now, for a small mirror, again, it doesn't really matter, but you can picture, as these numbers here reflect different rotation speeds at those different lines of latitude. If you have a big enough mirror, what that means is that the northern part of your mirror is moving, even though it's, maybe rotating at 10 miles per hour or something like that on the edge. But what that means is that Coriolis force means that the bit at the northern part of your mirror is rotating a little bit different, a little bit slower than the southern part of your mirror. And for a 10-meter class mirror, the difference in the rotation rate is about 1/20th of a millimeter per second. If you looked at the north pole of your 10-meter mirror and the south pole of your 10-meter mirror, if you're sort of at a mid-latitude range where most telescopes might sit. So 1/20th of a millimeter per second doesn't sound like a big difference, but it is enough to introduce effects of astigmatism and coma at that level of sort of 5 to 10 arc seconds, which is very significant, especially if you're at some sub-arc second world-class seeing site and you're building sort of a 10-meter class telescope. Now, again, we understand astigmatism, we understand coma. You could build a corrector that corrected for that astigmatism and coma. It would only work at a given latitude for a given size telescope, but you could do it. But again, we're building this in the backyard, I'll show you in a second, of my supervisor's house in Vancouver, where 5 to 10 arc second seeing was standard observing conditions. Very humid, very poor seeing, and it was also a 3-meter class telescope, not a 10-meter class telescope. So the astigmatism and coma is sort of hidden, but that does become quite substantial if you're thinking about at least a 10-meter class telescope. Again, things you don't have to worry about really when you're talking about solid mirrors. The other thing links back to what I said right at the very beginning. Because you cannot point your telescope at a particular object and track, it means that you get effectively the sorts of things you see there. You get star trails going above your image. Now, you can imagine if you're right at the North Pole or the South Pole and your telescope is pointing directly upwards, everything is just a nice little circle on your image. If you're sitting at sort of mid-latitude, if you're sitting right on the equator, this is not an issue because the star trails go right along the column if you're sitting right at the equator. But anywhere away from the equator, you start to get increased curvature in your star trails. And if you have a large field of view with a large CCD, then your star trails can arc across 2, 3, 4 pixels or so. And so everything will no longer sort of be circular, if you like, in your image. Everything will be skewed to the north or skewed to the south, depending on which hemisphere you're in. So this is something that you sort of just have to bear in mind that you have to deal with. So even if you are tracking your CCD at the sidereal rate, your objects will be arcing across the CCD. So you do your best to minimize it, and you don't get any blurring in the, if you like, the east-west direction, because you clock it at the sidereal rate. And for where we were in Vancouver, at latitude around 50 degrees, the CCD we had at the time, that gave us about a 20 arc-minute field of view, but it did mean that stars would arc across sort of 2 to 3 pixels. And so everything, don't worry about the details here, but things that would have this sort of Gaussian shape, your point spread function of your star, everything gets sort of skewed a fraction of a pixel to the north. And again, this is not something we corrected for, and I'll show you a picture of what the field of view looks like, and you can't see anything being skewed, if you like, to the north. But again, that's largely just reflects the fact that it was in a very poor seeing site. This sort of thing is sometimes called drift scanning, sometimes called time delay and integrate mode. It's used in the Sloan Digital Sky Survey. It's a very well-known technique of sort of not just integrating and then closing the shutter and reading out, but clocking the CCD at a specific rate to try to, if you like, smooth the noise over many pixels rather than just have an object sitting in just 1 pixel or 2 pixels for a long exposure. So that helps to reduce the noise if you allow the object to sort of move and shuffle the photons, the electrons from pixel to pixel to pixel in your CCD. But again, it's just the sort of thing you have to bear in mind, since you cannot track. Technically, all of your objects are going to have this skew to the north. Other things you have to think about that you don't have to worry about with the solid mirror is this is a liquid, and it's rotating. For the mirror that I made, a 3-meter class telescope, at the edge, you could just walk quickly. So it's about 3 miles per hour at the edge of the mirror was the speed that it's moving at. And so, thinking about it the other way, what that means is that the liquid is feeling a 3 mile per hour wind of the atmosphere above it. So it's wind shear, and it introduces a little bit of scatter. In that case, a 3 mile per hour wind, if you like, is blowing across the surface of our mirror as it's rotating. If you go to a bigger 5, 10 meter class telescope, you might be moving at 5, 6, 7, 8 miles per hour at the edge. So you have this wind blowing across it, and you get the shear layer instabilities. Introduces things called sailors would recognize. It's called cat's paws, and they're basically just little ripples caused by the wind flowing across. Now you can try to minimize it by putting, for example, a layer of mylar across your telescope as it's rotating, so that you get to the point where the air trapped between the mercury and the mylar is rotating at the same speed, and so you don't get those instabilities. This does become an issue with very large telescopes. But there are some mitigation things, and I'll show you one more before I finish up. How do we actually build one? So I've talked about a whole lot of limitations. How do you actually build one? What we did was my supervisor, Paul Hickson, he had an incredibly equipped garage that had all the equipment necessary to build this. He built his own private planes as a hobby. He had all the equipment to build a plane from scratch, and I did actually fly in one of them with him. Basically what you do is you take very highly dense styrofoam, which is what the base of the mirror is, and you cut them into octants, into wedges. You stick the wedges together. You take a hot wire and cut off the bottom to reduce the weight. You try to use a hot wire to cut roughly parabolic shape into the foam. You cover it with as many layers of Kevlar as you want. And then you spin it you attach it to a base plate and sit it on top of a frictionless air bearing, which is driven by a drive motor. And you start rotating, you pour some epoxy resin on, and you allow that epoxy resin to rotate exactly like you saw in the very first movie. You liquefy the epoxy resin, let it cool down while it's rotating, being a liquid, it takes the shape of a parabola, and you get something to a fraction of a millimeter, which is a very nice place to start. And then having cooled down and solidified, you've effectively got your liquid mirror. It's done. The only thing you need to do is put the reflective surface on. And so you rotate it again on the frictionless air bearing, pour on the appropriate amount of liquid mercury. You don't want to put tons and tons on because it's very heavy. This is the dark pit here is the liquid mercury. We typically needed between 1 to 2 millimeter layer across the surface of the mirror. If you didn't have a good base to start with, then you would need more liquid, which increases the weight, which increases the flexure. So you, again, to minimize the cost, you're trying to keep, and the flexure, you're trying to minimize the amount of liquid mercury that you need to put on the surface. But still, with a 3-meter class mirror, you're still looking at on the order of 20 liters or so. So again, that's where that 3 million pounds worth of liquid mercury, or 0 if you get it from an industrial estate, comes from. Just to show, before I show you our results, I'll just show you, come back to Robert Wood's work in 1908. This is the sort of the hand-drawn sketch of his setup in his farm in upstate New York, where he took a barn, cut out the roof, and here's the telescope pit. Here's his mirror down here with liquid mercury on it, driven by this drive motor over here, and access point over here. It worked. He was able to take some pictures and resolve double stars at the level of, I think, sort of 3 to 5 arc seconds or so in separation. So again, you're not talking sub arc seconds seeing, but it did work, and he was able to resolve, the quality of the mirror was sufficient to resolve doubles at that sort of level where the separation might be a few arc seconds or so. So it was a success. He sort of stopped at that point and stopped working on the liquid mirror telescope concept. So this is where I'll just show you the last few slides is what we actually did. When I started this project, like I said, I was seduced by how exciting it sounded. I didn't realize I was going to be doing a lot of hands-on work, as we were starting from scratch, like I say, in Paul Hickson's backyard. Everything from building the mirror cell from scratch to putting a concrete pad in his backyard and building a silo. This is the silo under construction. It's basically a garage door at the top there that opens and closes. That's our shutter, if you like. And that was sufficient to hold this roughly f2 2.7 meter mirror. The very, very, very first day of my postgraduate degree, I showed up, and as anyone who might know me, my wife would testify, I am not a handy person. But again, in a time when their risk assessments were non-existent, I walked in and Paul just handed me some 2x4 wood and a table saw and said, start to work and start cutting things. And it took probably about 10 minutes or so into the start of my master's before I had managed to, it was my first time using a table saw. It was great, having great fun cutting the wood. Made the classic mistake of reaching in to grab the wood. Not maybe fully appreciating just how powerful those table saws are, and managed to stick my finger into the table saw, turn my finger inside out. So within the first hour of my postgraduate master's, I was sitting in the waiting room waiting to have my finger reconstructed, and I still bear a lovely scar to this day. So I'm sure my supervisor was thinking, what have I got myself into? It's taken minutes for me to have to take him to hospital. Still wasn't enough to get on the radar of anyone worried about health and safety. And then a few months later, building this dome, if you like, the silo, I managed to, we were doing the painting here, and I was shuffling, this is me sitting here, moving the ladder. The ladder had some 2x4 again, sitting, resting on top of it. As I moved it, this 2x4 fell down. You can see none of us wearing helmets or anything. I cracked open my head. This was just a week or so before I was getting married, and so all of the wedding pictures are always from the front. There is nothing from behind. So imagine how thrilled my wife was to see my head having to be reconstructed. After my second time in hospital, realized I was not going to continue doing instrumentation. Decided theory might be a better place to put my skills, and so I moved into the development of software related to analyzing the data that this telescope was going to be gathering. But despite all those issues, we did actually get a mirror that worked. Here it is in the lab, and here it is inside the silo. 2.7 meter diameter. These things are amazing. They're, like I said, rotating at basically walking speed if you walked around the outside. If you sort of blocked off your eyes and just looked from the edges and just looked at the mirror, provided there's no bugs stuck in it going around, you cannot see any evidence that it is anything other than a perfect mirror. You can't see it rotating. You sort of know in your head that that's going to be the case, but it's not until you actually stand there and look at this mirror and realize just how perfect it is, as good as any professional quality glass and aluminized mirror that is out there. And indeed, when you measure it in the lab, take our 2.7 meter telescope in the lab and do all the things that you would do with, say, the Hubble Space Telescope. It is what we call a diffraction limited mirror. You could not make this any better. It has a high Strehl ratio. You can see the airy disk, and the interferograms show that it is effectively a perfect mirror, and the quality of it is as good as the Hubble Space Telescope mirror. So at least in terms of what you get in the lab, you can design fantastic, beautiful mirrors, despite all the sort of limitations that I talked about. How does it actually perform in the field? Well, this is, again, just showing a sort of a snapshot, just a 20 by 20 field of view. There's nothing, particularly important about this. This is just a 2-minute integration as it scans across, again, reading it out during that 2 minutes at the sidereal rate. So everything kind of looks circular the way it should. Now, again, the seeing in here is very bad, so you don't see any of the astigmatism and coma and the things that you would see if I had done the exact same experiment at the top of Mauna Kea in Hawaii, for example. But so it works at that sense. It does look like astronomical data, which is good. What our goal was to take let's say you had a beautiful 8-hour night, and you you read the CCD out at the sidereal rate. At the end of the night, you would have an image which was 20 arc minutes wide and 8 hours long, a long, thin image that wasn't particularly deep, but effectively, in our case, 2-minute image across this large area. So you would put a particular filter in one night that might be a narrow filter around 4,000 angstroms in the blue. Then the next night, we put another filter in and do exactly the same thing. And then the next night we put another filter in and another filter in. And over the course of, say, 40 nights or so, you would build up a low resolution spectrum of every object in the sky. So if you're interested in surveying the physical characteristics of everything in the sky, at least in a statistical sense, where you don't care about the objects that are in that direction versus that direction, just looking straight above you, this is the right sort of facility for doing survey work. Very, very cheap, and allows you to build up these low resolution spectra. Now, what I've discovered, as I'll show you in a second, we didn't really advance a whole lot beyond that. And the technique of liquid mirror telescopes hasn't really taken the world by storm. But the technique that we sort of invented to do this building up low resolution spectroscopy using these narrow filters and building up a spectrum over the course of many, many, many nights has now been adopted in a number of surveys that are ongoing now, using, say, the 3.5 meter Calar Alto telescope in Spain and a equivalent facility in Brazil. So these surveys called Alhambra and J-PASS have taken the technique that we invented for the liquid mirror telescope survey and are now applying it using traditional mirrors as well. So even though the liquid mirror telescope concept didn't take off, the methodology of characterizing the physical nature of all of the objects in the sky has been embraced by the communities. I did mention, just before wrapping up, the sort of the safety aspect. Now, the details here don't really matter. This is just showing you, for example, how much mercury vapor, which is this curve here, measured in milligrams per cubic meter, as a function of time. So liquid mercury is nasty stuff. The vapors are very dangerous. The current working limit by the World Health Organization, at least up until 70s and 80s, was around 0.05, this number here. Now what you can see is that this is for a normal work day. So for liquid mercury in the telescope, if you were inside the silo for the first few hours, you're well above the limit, the recommended safe limit. Now, you can see as time goes by, it settles down and drops below that. Current standards actually put the number down closer to 0.01 or so. Now, the reality is, once you've established the surface, you don't need to be in the silo. So you need to be there to establish the surface, because it's very, very fiddly and very, very frustrating when you're trying to make a very, very thin layer. And occasionally the surface breaks and puckers, and then once you get instabilities, it goes all crazy. But once you've got a stable surface and it's closed, you don't need to be in the silo the rest of the night. You're sort of done. So you're always wearing a mask. You've got a mercury sniffer to make sure what the levels are at. What it also helps is that you actually get there's a thin layer, think of an oxidation level, layer that gets established on top of the mercury when it's stabilized, and that actually helps reduce the evaporation of the mercury and doesn't affect the reflectivity. So it doesn't become particularly dangerous after a few hours or so, but it is something to be aware of, and you have to be monitoring all the time when you're working in there. So what's happening today, just to sort of wrap up, not a whole lot. It worked. We got some data. We published a couple of papers, not particularly anything impactful in a scientific sense, but the first real demonstration that you could collect useful scientific data, measure some redshifts of some of the objects, get some basic characteristics of stars that are in the field. The technique got a lot of attention when we sort of developed it in the late 80s. We built a couple of them for atmospheric research groups. There's still one that, if it's not still operating, was operating very recently at University of Western Ontario in Canada in their LiDAR facility. LiDAR is kind of what you see here. You fire a laser up into the atmosphere, and you look at how that laser scatters off of different layers up to sort of 80 miles or so. You can measure the characteristics of clouds, aerosols that are trapped in the atmosphere. And basically what you need is a laser to fire up, and then just a big light bucket that measures the scattered light. So they don't care whether you're pointing in that direction of the atmosphere or that direction. They're just looking straight up to do their study. So we built a couple of those for LiDAR groups. And that we also were subcontracted by NASA to build one for in New Mexico at Cloudcroft, where they have a orbital debris monitoring station. So they have a number of different experiments going on in Cloudcroft that are measuring just how much space junk is up there. And so that operated for, 10 years or so. I think if you go to the Cloudcroft page, to the orbital debris program, you can see in amongst the missions, the Liquid Mirror Telescope that was a clone of the one that I built for my master's. It's a 2.7 meter class telescope where they just look straight up night after night after night after night. They obviously can't track particular debris, but they can just look at the statistics of debris. And that was the whole gist of it in parallel with a lot of the other experiments that were going on. So again, both of those were operating until fairly recently. Not a whole lot out there in a astrophysical sense. We did get to the point where we moved beyond 2.5 meters up to a 6 meter telescope, which I'll show you in a second. What you will notice is no matter how careful you are, you do have to be doubly careful that this thing doesn't tip over. You are balanced on an air bearing and supported by a base plate and rotating. But like I say, if a bat or something lands in here, it breaks the surface. And then as soon as you break the symmetry, all of a sudden these sucker holes just grow really fast and it wobbles. And if you don't have something in there to catch it in a catastrophic case, well, then you're in trouble as well. You do have various posts right underneath it so that if it does get unbalanced, it doesn't just spill into the spill tank, but you do have to build that into place just in case. So it was one of our nods to safety, if you like. Then this is where we ended up. This was a 6 meter LMT at University of British Columbia. Now, much more cognizant of health and safety and risk assessments, all built with the approval and done properly with the university. It's built in the research forest that University of British Columbia owns. It's nestled right against the edge of the mountains, so it's just about the worst place that you could build a telescope. All the weather comes in from the west coast, hits those mountains and dumps. It was never really used for any scientific purposes. And towards the end of its life, up until a couple of years ago, where it was finally shut down, it was mostly just there as a museum piece. So if you were there as part of the tour of the research forest, you could arrange to go in and see the Liquid Mirror Telescope in operation. But it works. You could build a 6 meter class telescope. But at the end of the day, if you look at telescopes, large telescopes today, Back then when I was starting this, whatever, 30, 35 years ago, whatever it is now, when you looked at the cost of large telescopes and professional telescopes, the mirror was a big part of the cost, and it's why we had to come up with clever ways, not just monolithic spin casting that we saw at the very beginning, but using segmented mirrors like we use in most of the large mirrors nowadays. And what that meant is that the cost of the mirror came down dramatically. Where the real cost with large telescopes comes, it's not the mirror itself, it is all the associated equipment, the spectrographs and imagers and correctors and the dome and the ventilation and the air conditioning. Everything that goes with it is where the really big costs are. It's less about the mirror itself. And so once the cost of contemporary mirrors came down and the associated instrumentation went up, it took away the main selling point, if you like, of a liquid mirror telescope. So it went from something that looked promising 35 years ago as a way to build a very cheap survey instrument, but technology around us caught up, and it meant that they became sort of somewhat obsolete as an alternate to the classical glassless aluminized mirror. So in some sense, I've sort of answered the question as to where I started with whether it was the wave of the future or a ripple. Don't think it's the wave of the future. It may be, in hindsight, a ripple, but it was a fascinating ripple, and it was a fascinating ride for me to be involved with, particularly being a theoretician and not really being someone who was particularly advanced at hands-on instrumentation development. So it was a fantastic ride for me. Got a lot of great papers out of it that really set me up in my future career, even as I moved from instrumentation into theory and computation. So I'm not sad about the decision to pursue it, although depending on the day you catch me, I do go back to that very first slide once in a while and think, what if I'd stayed with extrasolar planets? Could I have been the person who stood up there a couple of years ago and won that Nobel Prize for the first development? It's 2020 hindsight now, and so I'll just end by saying thank you very much for listening. I really appreciate it.
Brilliant. Thanks very much, Brad. That was so interesting. The engineering to be able to spin that without producing vibrations itself must be quite challenging.
Super challenging. Where we were building it in his backyard, it literally was his backyard in the suburbs of Vancouver. You had to worry about things like garbage trucks going by, large lorries going by, vibrating things, and that sets up ripples, which increases your scattered light. It's at sea level, like I said, with more bugs and mosquitoes than you could possibly imagine. And as soon as any sort of bug landed in there, it would stick. And once that happens, you get this sort of puckering around the bug, which introduces scattered light. So these are sort of unique challenges maybe you wouldn't face when you're working up at 4,000 meters or so in Chile or Hawaii.
Fantastic. Anybody got any questions for Brad? You should be able to unmute yourself, so if you've got a question, please.
Yeah, Brad, it's Kevin here. That was a great talk. Really enjoyed it. Thank you. This is probably a silly question, and I'm sure if it would have worked, somebody would have thought of it before. But if I remember correctly, near the start of your talk, you were saying that to avoid the hazards associated with mercury, that gallium was a possible alternative. But one of the drawbacks of gallium was the freezing point.
Yeah.
Was too high. Potentially or conceivably, could it work that you allow it to solidify while rotating, and then just have it as a solid mirror at room temperature?
Yes, you could, and that, I guess effectively, that's just replacing, the molten glass with freshly aluminized surface on it with a solidified gallium. You're absolutely right that you could absolutely do that, long as you're, if you just use pure gallium, of course, 30 degrees centigrade. So you got to make sure your temperature doesn't creep up too high.
Sure. Yeah.
30 degrees, or you're going to wake up the next day and your mirror is a pool, if you like. But yeah, you absolutely could do it. Whether you would do it, probably not.
Yeah, sure. Yeah. Say it's more a theoretical exploration.
Yeah. And it is really all of it is really fascinating from a theoretical standpoint, even if it didn't replace the classical aluminized mirror. And a lot of people, there's a big literature out there, not just the astronomical community, but other communities looking at what could you do to make these things, in theory, more useful. In the optics community, one way you can do it is you can design incredibly complex correctors at prime focus that aren't just, we don't really have a corrector. We had a 20 arc minute field of view, and that was fine. But if you wanted to open up, potentially a much larger field of view to maybe, you could go out to 20 degrees probably in your field of view. Again, it's not the full 180 degrees, but you could get a reasonable field of view potentially. But the cost of we actually had some optical folks draw up what it would actually look like for that particular mirror that we had. But it got into the millions of pounds level very quickly, because it was if you want a really big field of view, it's a really complex optical design with multiple segments stuck together and cemented together. So that was one way to try to make them more functional. The other way, you can start to get more clever. And I find it fascinating. You could do things like, if you had a magnetized liquid, for example, and you have it rotating, and then you have underneath it a whole bunch of some sort of piezoelectric devices that change the strength of the magnetic field right underneath the mirror. And so if you have it sort of, you have this liquid that's rotating, and then you turn on your magnet and allow it to adjust the magnetic field across the surface of the mirror, it would allow you to tilt further and further, but you would adjust the magnetic field on the fly to make sure, even though it was rotating, the magnetic field kept it in its parabolic shape. These sorts of things are theoretically feasible, but again, the technology involved becomes, prohibitively, crazily expensive and complex compared to a simple glass mirror. But and other people, again, this is way outside my area of expertise, are people who thought about, forget about rotating, just have a flat liquid that's sitting there, and you have some magical way of changing the surface, kind of the index of refraction as you go across the surface, by changing the fundamental characteristics of the liquid as a function of radius. So you'd have a flat mirror, and light would come in, and it would effectively mimic having a parabola and give you an image by taking things in flat and sort of pulling them in by changing the index of refraction across the surface of the mirror. So it would still be liquid, but you would be on the fly changing the radial index of refraction, which does change the way light bends when it hits the liquid. So mimics kind of a lens effect. So there's a whole literature out there that also looked really fascinating, never got turned into reality, at least in terms of an astrophysical sense.
Great, fascinating. Thanks.
Dave, you got a question?
Yeah, I was just going to ask, well, first of all, an amazing project. I didn't realize it went back so far, 1920. That's some history there.
Yeah.
I'm just curious, what magnitude were you reaching? Yeah, I think you said 2 minutes exposures. That was on a strip.
Yeah, so the paper is published if one does Google it. I think it was on. So I think that was on R of 21. So it's not super deep, but it is super shallow. Again, the image, you're probably in the worst site in Canada for a telescope. So you're not particularly deep and not particularly competitive with a lot of conventional telescopes when you're looking at that. But it was more just a demonstration of the concept, if you like, rather than anything particularly functional.
Yeah, but it's amazing what science you can do with short exposures. You got the aperture. Just
having the sheer volume of the sky. Nowadays, it's a bit different. We have, 30 years later, we've got these telescopes that have giant fields of view that the next generations, be scanning the entire night, the entire sky every night. Large synoptic survey telescopes, going to be covering the sky back and forth with 8-meter class telescopes. And, 35 years ago, these things were just a pipe dream. And so this was just, can we get something to market very quickly that would give you some statistical coverage of the sky, to do some basic statistical survey of the sky. But then, shortly thereafter, you had things like, again, Sloan Digital Sky Survey and other things came along and sort of, again, made this sort of thing a little bit obsolete in some sense.
Just to finish my questions, what about the health and safety of using mercury in such a large area? Mercury fumes, mad as a hatter and all that?
Yep. So
does that explain anything at all?
Yeah, the one slide there towards the end where show the now. Okay, for the first 2 years I was working on it, it was all about designing and building both the dome, the tripod structure, even things like I didn't know anything about air bearings before, but purchasing an air bearing, and then you have a drive motor that spins it at a very precise rate with a bit of magnetic tape between it. I learned a lot during that process, but throughout that process, I didn't have to worry about the liquid mercury because it was still theory at that point in time for me.
Yeah.
So my initial papers are all things like what are the optical characteristics that you might expect, the stuff about astigmatism and coma, the curvature of the Earth, all these other things. My first paper was really more structural engineering. It was the stresses and strains as you put more and more weight on the thing. How much does it flex, and then therefore how much more liquid you have to put on to keep a nice parabolic shape. It was really almost like the very last day of my master's project where we actually poured liquid mercury onto the surface. By that point, we were using masks and things like that. But by that point, I said I was checking out. I wasn't doing this anymore. So I left that to my supervisor and the next generation of students who took it to the next stage. And I just stayed on the software development side of things and decided to remove myself from it. But yes, you're right. You have to be careful when you're in there to make sure you're wearing a mask. In theory, you just pour liquid in, you would turn on the drive motor, this thing would spin at the appropriate rate, and it's a liquid. It'll settle into the shape of a parabola. The problem is because you're trying to do it with such a thin layer to minimize the weight. As I said before, it really is kind of a black art to be able to establish the surface. So you have to, the first time you spin it up, you have to be there with your mask on, leaning out over top of it and lovingly caressing the mercury to thinly coat the layer, because as soon as you get that, like I said, a bug landing on it or an asymmetry in the way that it's spreading out, then it quickly gets unbalanced and it all runs apart. So getting it to once you get the surface closed, surface tension wins and it sort of held it in shape. But if you had to stop it and respin it up, it was a challenge.
Thanks, Brad. Thanks.
I was going to tell you just one before. I'm going to say one more thing, that kind of a health and safety thing as well. This is all pre 9/11, so airport security was a whole lot different than it was post 9/11. One of the things that I needed, we bought the air bearing was, that was the single most expensive thing that we had to buy. That was fine. That was shipped to us. But the drive motor is just a standard drive motor. It's kind of like this big and it's got a spindle on it. And what we did was we contacted our colleague in Quebec, this Romano Bora from Liquid Mirror Telescope fame, and he had a spare drive motor. So I flew into Quebec to pick up the spare drive motor. I was there for a few days, and when I came back, checked in at the airport in Quebec. This thing was a big, heavy thing. I didn't want to put it in my luggage, my check luggage, so I just took it in my carry-on. And you would never do this nowadays. You would get pulled over and arrested because, the guy, he pulls it out, it wasn't a photographic film or anything like that. So I just left it in my bag. It went through the X-ray scanner, comes out the other side. And, they pull out this thing that, looks for all intents and purposes like a bomb. And they say, well, what is this? And I said, it's a drive motor for Liquid Mirror Telescope. He's, yeah, okay. They just let me onto the plane. Again, not a chance in hell you'd ever get away with something like that nowadays. But it is one of the humorous memories I have of the experience.
Fantastic. Another thing I thought of, Brad, if you're using different metals as a mirrored surface, does it affect the wavelength they reflect at all?
Yeah. In fact, I should have a picture of that. So liquid mercury, if someone Googled reflectivity curve for mercury, it does have a sharp cutoff point, and can't remember now if the sharp cutoff point is at the blue end or at the red end. So it's not as good as, I think, freshly illuminized mirror has a greater wavelength coverage. I just can't remember where it drops off, but you're absolutely right. There is some point there where it wouldn't be useful. I just can't remember, is it the ultraviolet or the infrared, but there's some place where it wouldn't be a useful reflective. But at least, for the most part across the optical range from sort of, from the blue to the red in the normal sort of 400 to 700 nanometer range, it was fine wherever it drops off, but it does drop off somewhere which is not wildly outside of that.
Yeah. Okay, brilliant. Okay, any other questions for Brad?
Yeah, I've got one. Was any consideration given to perhaps something based on a heliostat type design to give you more flexibility, or does it just blow the cost out the water so you don't even go there?
How would you do that? What do you have in mind?
Well, I was thinking, the way a heliostat works is you have a separate mirror outside, which is tracking what you want to look at. So it gives you the ability to look other than straight up. But obviously it would be a big mirror.
Yes. I'm trying to think of the other sorts of designs that I've seen. So you would. So yeah, I cannot think off the top of my head. Hadn't encountered it. It might just been a lot of years since I worked on this myself, but it's not ringing a bell. No, I can't really think of anything. And I read some of the literature that I alluded to. I read out of sort of passing interest, but everything that I read that tried to extend its applicability into the real world in some sense just came at a steep financial cost. And so the single thing that drove us right at the beginning was, can we keep it less than £10,000? And modulo the fact that you weren't paying for labor costs because we were just cheap postgraduate students. But that aside, it was keeping the hardware costs, if you like, to £10,000, which was done successfully. But anything else that I saw in the literature, the complexity just went up orders of magnitude and just blew out the cost and made it prohibitive. So.
Right.
Okay. Any other?
I was just wondering, you said something about magnetic liquids. Wonder whether you could do something like adaptive optics with that.
Yeah, I know. I mean, I sort of understand conceptually what they're doing or what they're talking about. I don't know if one tried to do this in reality, how fine-grained your ability to control the magnetic field would be. You've got some 5-10 meter class mirror. Do you need to be able to control it at a fraction of a wavelength across the entire surface? When people do at least things like active optics, you just have actuators on behind these segments, and so you only have to have things good at the level of once every segment to make these sorts of active optics corrections. I don't know with these magnetic fields, would you have to have a trillion little magnets behind there that you can control, or can you do it with hundreds of them in some clever way? I have no idea. It feels in my head to have a really high quality mirror that you would have to have a horizontal magnetic field that was precise, again, to a fraction of a wavelength horizontally across the surface. So you somehow need to have a really fine magnetic field on really small scales. So it sounds great in theory, and maybe some clever person can do it, but it's, again, sort of way above my pay grade.
And mine.
Okay. Any other questions for Brad? No? Okay, well, Brad, thank you very much for giving up your time tonight.
Absolutely. Had a great time. Good to see you all.
Fascinating
Thank you very
talk.
much.
It was a blast from the past. I have a series of talks that I do from much like Julian, you got a reserve of talks that you can pull upon depending on what you feel like talking about on a given day. And I started to think back on my career, what was something that was not really part of, in any way, shape, or form, the stuff that I talk about. And I thought, I worked on this liquid mirror telescope. People are always fascinated about it. When I've gone to astronomical societies, people have, delved in, Googled my name or something, and people were reminding me about the liquid mirror telescope. And I thought, well, enough people were asking me about it. I thought, okay, maybe I need to pull all of these threads together and try to pull it into a talk. And it was a lot of fun revisiting it and going back over the old literature. So I really enjoy, even though it's not something I work on now, I really enjoy the opportunity to talk about it.
Yeah, it's a fascinating story. Thanks very much.
No,
excellent.
Thanks very much, Dave. Thank you all for giving up your evening. I appreciate it.
Yeah, fascinating. Thanks.
Thank you.
Thanks,
Good to see you all.
Okay, so it's that time of the meeting again. So
I'm going to